Hello, dear students. Here we start with the third type of Diophantine equation, which is of the type x raised to 4 plus y raised to 4 equal to z square. Okay, so up till now we have studied two types of Diophantine equation. One is a linear Diophantine equation, second is a Pythagorean triplet, and now this is the third one. So here we are going to show that this Diophantine equation has no solution in positive integers. Okay, so we cannot find out the solution of this Diophantine equation of this type of equation in positive integers, but though its solution does not exist, that concept itself, that concept is very important and very useful also for proving the many other results. Now before I start with this proof, I just wanted to recall two things. One is, all of you know that square of an integer is either congruent to 0 or 1 modulo 4. That means the square of an integer is never congruent to 2 or 3 modulo 4. I hope all of you know this, because if you suppose consider x is an even number, then x square is equal to 4m square, which is congruent to 0 modulo 4. If you consider x is an odd number, then its square is equal to 4m square plus 4m plus 1, which is congruent to obviously 1 modulo 4. And therefore square of any number is either congruent to 0 or 1 modulo 4. If we get some square which is either congruent to 2 or 3 modulo 4, then we say it is something absurd. Okay, so this is the concept which we use for proving the results, and also the theorem which we have proven for a Pythagorean triplet. So what we have proven for a Pythagorean triplet, that the Pythagorean triplet x square plus y square equal to z square has a solution with x is equal to 2st, y is equal to s square minus t square, and z is equal to s square plus t square. So we have proven that for a given Pythagorean triplet, there exists integers s and t with s greater than t greater than 0. S and t are of opposite parity, and therefore they are also they are relatively prime. And x, y, z with this value satisfy the Pythagorean triplet. So this concept or this result we are going to use for proving the theorem on the Diophantine equation of type 3. So please remember these two things, and let us start with the proof. Okay, so here we have to show that it has no solution in the positive integers. So here here we start with the wrong assumption, and then we arrive at a contradiction. So what is the wrong assumption? Here we say that let if possible x0, y0, z0 be a solution in positive integers for this given Diophantine equation with z0 as the smallest value for z. So please remember this condition. This is the condition which we use to get the result that we arrive at a contradiction, because we get some different solution for x raised to 4, y raised to 4 equal to z square with the value of z as less than z0, and then we say we arrive at a contradiction. Okay, so here we have we consider x0, y0, z0 as a solution with z0 as the smallest value for z among all other solution. That means suppose if x1, y1, z1, okay, or if x2, y2, z2 are another solution for x raised to 4 for y raised to 4 equal to z square, then z0 is less than z1, z0 is less than z2, and so on. So z0 is the smallest value among all other solutions. Then firstly we will show that with this condition, then x0, x0, y0, z0 must be relatively prime. So here also we have to show that they are relatively prime, but then we are assuming that let it possible they are not relatively prime. That means they have the GCD d which is greater than 1. Then by the definition of GCD, d divides x0, d divides y0. Therefore, d raised to 4 divides x0 raised to 4, d raised to 4 divides y0 raised to 4. Therefore, d raised to 4 divides their sum, but their sum is equal to z0 square, because it is a solution of x raised to 4 plus y raised to 4 equal to z square. So therefore x raised to x0 4 plus y0 4 is equal to z0 square, and therefore here we get d raised to 4 divides z0 square, therefore d square divides z0, that means z0 upon d square is an integer. Now since x0 y0 z0 is a solution of this Diophantine equation, it satisfies this Diophantine equation, and therefore we get over here that x0 raised to 4 plus y0 raised to 4 equal to z0 square. Now divide this equation throughout by d raised to 4, then we can write it in this form. Okay, so here what you can observe that then x0 by d, y0 by d and z0 by d square is a solution of this Diophantine equation. Now this is a solution. We know that z0 by d square is an integer, so obviously z0 by d square is going to be less than 0. So it is a contradiction to our assumption that z0 is the smallest positive value for z among all other solutions. So we arrive at a contradiction. Therefore our assumption that GCD of x0 y0 z0 equal to d greater than 1 is wrong, and therefore the GCD of x0 y0 z0 is equal to 1. Therefore I am telling you that this condition you have to remember, that z0 is the smallest value for z, because this this is the thing which we are going to use for proving that whatever our assumption is a wrong assumption. Okay, so first part we have completed, that we have proven that x0 y0 z0 is the solution, then their GCD is equal to 1. Now with that condition, now we proceed further. So this is the part. Therefore x0 y0 z0 is a primitive solution of x raised to 4 plus y raised to 4 equal to z square. Now this x raised to 4 plus y raised to 4 is equal to z square, with the solution x0 y0 z0 we can write it in this fashion. Okay, and therefore now what we are getting, that x0 square, y0 square and z0 is a primitive solution of x square plus y square equal to z square. That means now over here we are considering the solution of a Pythagorean triplet. So x0 square, y0 square and z0 is a solution of a Pythagorean triplet. So since it is a solution, now as I already told you, we have you have to recall the theorem which we have studied for a Pythagorean triplet. So therefore using that theorem we can say that there exist integers s and t such that s is greater than t greater than 0, s and t are relatively prime, and x0 y0 x0 square y0 square and z0 is a solution. So their values are given by these numbers. Okay, so here we are just applying that theorem. Now so we are calling this as 1. So here we know that s and t are again of opposite parity, so one of them is even, other is odd. So let it possible s be even and t be odd. So when s is even, obviously s square is congruent to 0 modulo 4, and when t is odd, t square is congruent to 1 modulo 4. So we have that y0 square is equal to s square minus t square. So here s square is congruent to 0, t square is congruent to 1. So s square minus t square is 0 minus 1, means y0 square is congruent to 0 minus 1, which is congruent to minus 1 modulo 4, which is congruent to 3 modulo 4. So this is a contradiction, as I explained you in the beginning, that square of any number is either congruent to 0 or 1 modulo 4. Here we are getting it is congruent to 3 modulo 4. Therefore here we arrive at a contradiction, and therefore here we consider that s is even and t is odd is wrong. So remember, over here we have to take as s is odd and t is even. Now when t is even, we take the value for t is equal to 2r, because t is an even value. So consider this as a equation number 2. So all these equations which are numbered are important because we are going to use them. Okay, so remember over here the value of t is equal to 2r, where what is t? T is an integer, where it is one of the part of the Pythagorean triplet x0 square, y0 square and z0. Okay, so with this now we proceed further. Now page number 17. So here we have s0 square is equal to 2st from 1, because there we have defined the solution, correct. So put the value of t as 2r, so you get it is equal to 4sr. So you get s0 upon 2 the whole square, just simplification of this, is equal to s into r. But what do we know about s and t? S and t are relatively prime, and we have over here t is equal to 2r and s is also odd. So S is odd, T is equal to 2R, and S and T are relatively prime. Therefore, obviously, S and R are also relatively prime. So S and R are relatively prime, but their product is equal to the perfect square, and therefore each one of S and R must be a perfect square. So here we say let S equal to S1 square and R equal to R1 square. So from 1 means where we have defined the values for x0 square, y0 square and z0. So from 1 we get y0 square is equal to s square minus t square. Therefore s square is equal to y0 plus t square. Okay, now here by mistake I have left this remaining part of the page. So now let us move to the next page, that is a page number 18. So over here on the, see student, here you have to remember certain steps in this proof, that means there is no continuation. Okay, so here uh, uh, we have got so in the previous page, sorry, what we have got, that y0 square is equal to s square plus t square. Therefore s square is equal to y0 square plus t square. So this is again a Pythagorean triplet we are getting. Okay, so that is what we have mentioned on the next page, that therefore t y0 s is a solution of a Pythagorean triple. Okay, so since it is a solution, again we apply the same theorem. So the same theorem we are applying for two times. Okay, so now here we are applying the theorem for t, y0 and s. So t, y0, s is a Pythagorean triplet. Therefore again applying the same theorem, there we have already used the letters as s and t. So here we are using the letters as u and v. So there exists integers u and v, so that u, v are positives with the condition u greater than v greater than 0, and u and v are relatively prime, that means they are of opposite parity. Then same theorem we are applying, t is a even value, y0 is equal to u square minus v square, and s is equal to u square plus v square. So call this as equation 5. Then here therefore we get that t upon, since t is equal to 2uv, we get t by 2 is equal to uv, but we know that t is equal to 2r, we have defined already in the equation 2. Okay, we have defined in the equation 2. Please now I will not go again on the previous page. You please see while reading it, that t is equal to 2r, that is from the equation 2, and therefore here we get t by 2 is equal to r, it is equal to uv. Again what we have defined in the equation 4, you must be remembering that we have defined in the equation 4 as s is equal to s1 square and r is equal to r1 square. We have got s and r as a perfect square, so that is what we are using over here, that uv is equal to r1 square. Again we apply the same concept, that again u into v is equal to r1 square, but u and v are relatively prime, therefore u into v is equal to perfect square, implies u and v must be perfect squares. So that we are defining as u is equal to s1 square and v is equal to y1 square. Okay, so now we have got the values of u and v as a perfect square. Put those values in the equation number 5. Okay, so that we get over here s is equal, in the equation 5 we have s is equal to u square plus v square, but we know that as I have already recalled over here from the equation 4, we know that S is equal to S1 square, U is equal to, here we have considered as x1 square, therefore here U square is equal to x1 raised to 4, V square is equal to y1 square of y1 square, that is equal to y1 raised to 4. Okay, and therefore we have got here the equation as x1 square is equal to y1 raised to 4 plus is equal to x1 raised to 4 plus y1 raised to 4. Therefore here we have now got another solution as x1 y1 s1 for x raised to 4 plus y raised to 4 equal to z square. Now we already have one solution as x0 square y0 square we already have one solution for x raised to 4 plus y raised to 4 equal to z square as x0 y0 and z0, with z0 as the smallest positive value among all the solutions. So here we have got another solution. Now as I told you, here we are going to get the contradiction by showing that S1 is less than Z0. If we get S1 is less than Z0, then we arrive at a contradiction because we are saying that Z0 is the smallest positive value for Z. So now let us see how that contradiction do we get. So here we have S1 as positive number, correct? So it is less than S1 square, but S1 square is equal to S, that we have already seen from in the equation 4, correct, that S1 square is equal to S. Now again S is less than S square, clearly S square is less than S square plus T square, but we know that S square plus T square is equal to Z0, and therefore we have got over here S1 is less than Z0. So here we have got another solution for x raised to 4 plus y raised to 4 equal to z square with the value of z equal to s1, and we have got that s1 is less than z0, which is a contradiction because z0 is the smallest positive value among all the solutions of x raised to 4 plus y raised to 4 equal to z square. Therefore our assumption is wrong, and therefore there does not exist a solution in positive integer for the given equation. I know that this theorem is very difficult to remember, so you have to practice a lot for this theorem. You write it 4 times, 5 times, then only it is possible for you to remember. Okay, so please go through this, read it again and again, listen to this video again and again, and if you have any difficulty or doubt, you can ask me anytime. Thank you very much.